back to the new quarter. And this morning, let me mainly introduce you to the topic of energy storage. This is the topic I've been doing for about 5 years with actually very big effort in this area now. I also like to introduce my student, Matt, sitting right there. Matt will be speaking to you about why he likes to do energy storage research. I also like to mention that there's a class I'm teaching this fall quarter on the batteries, giving you an idea. How do you think about energy storage? What's the fundamental principles? What's the state of the art? What are the problems people care about? Let's see. Okay. But before I move on, I want to show one slide. I figure there's a lot of people from different departments might not know about my research areas. So this is my whole research group. Overall, this centers around the idea, how do you design the nanomaterials to impact different areas of fundamental science and as well as technology. Our core expertise lies in designing nanomaterial nanosynthesis, and we look into photovoltaics, energy storage, and environmental technology. We are also interested in a topic such as a very exciting new area called topological insulators. And that's mainly for fundamental science. And all this topic is very, very similar. The fundamental idea is try to identify the critical problem and then to think about whether you can solve those problems by the materials design. So today is only one type of example on energy storage, give you an idea how we think about energy storage. So I'm going to just focusing on, how do you do electrical energy storage? Of course, there's a thermal energy, there's a mechanical energy, there's also photons if you can store. So I'm speaking about today is only electrons. In the big picture, there are different ways to do it. It can be physical way, such as capacitor-based, ultracapacitor, supercapacitor-based energy storage. There can be electrochemical based, involving building chemical bonding, but with electrons coming in. That's batteries. There's also idea how do you do it purely in a chemical way. So that's for generating the fields. That is a lot of active research at Stanford on these topics. So today's topic is just on physical and electrochemical storage. And that's my main research topic. Indeed, today I'm going to only give you an example on the batteries, on the electrochemical energy storage. So certain things you need to know about energy storage before you move on. Let's define those parameters first. You heard about energy density or a specific energy. Energy density refers to how much energy you can store per unit volume. That's often very important for your cell phone, for your laptops. The volume matters. The weight actually doesn't matter as much, but the volume matters because you have limited the volume you can carry. Specific energy can be quite important for cars, because when the battery is very big, you care about the weight, so the energy per weight becomes important. Power density and specific power has similar definition. Now you need to differentiate between energy and power. Energy is total amount of energy. Power is how fast can you take out and put in the energy per unit time. So if you look at a car, energy density or specific energy determines how far your car can run, but the power is really related to how fast you can accelerate your car. So it's a different concept. Cycle life and calendar life is very important. For your cell phone and laptop, you need 500 cycles. After that, you still have 80% of capacity retention. For a car, you need 3,000 cycles. Calendar life for portable electronics, you need 3 years. For the car, you probably need 10 years. Safety, we know battery can explode, so safety is very important. The cost is very important. We don't think about that much for portable electronics. But when you buy 7,000 batteries and your electrical vehicle, you do need to think about the cost. At the end, with so much effort going into energy storage, and related to electrical vehicles, related to the electrical grid. And we pump in so much energy into those energy storage devices. We want to take them out, take this electricity out. The energy efficiency becomes important. That's defined as how much energy you put in, how much you can get out, what's the ratio of getting out versus putting in. Typically, for the battery, it's around 85 to 90% range. Can you get this to 99%? That's a very big question. So speaking of anything related to energy, that's so application oriented. You've got to understand what application needs first before you move on to go do your research. You want to know what's the parameters. That's most important. You want to tune those parameters. Let's look at portable application. As I said, it's the energy density, specific energy. That's the energy per unit weight or volume that's important as the first parameters before you talk about other parameters. Of course, the cost is very important. The reason is very simple because you carry this device with you. So the size and the weight is important. But for stationary application connecting with grid, solar, and wind, this is different. It's the cost jumping out as the most important parameter first before anything else comes. And how much power you can have to handle the fluctuation is also important. So now you look at these parameters and go back, you say, wow, now this becomes clear. What's the primary parameter, what's the secondary parameters? Let me give you an example. Today the time is short. Let me just focus on the high energy batteries. How do you do it? And let's analyze the state of the art. We know the energy is determined by how many charges you can store in the voltage, divided by the weight or volume. And the current technology, the best battery using lithium ion as the storage ions. So negative electrode is a graphite, positive is a lithium manganese oxide. Can you increase this dramatically? It's really, at the end, the problem of new materials. For the negative electrode, there's possible choice of these materials, which can provide up to 10 times more charge storage capacity. Positive electrode is sulfur and the air, also with very high capacity. At the materials level, you have a choice, but now you need to understand what are the problems. This is existing material using carbon. 6 carbons store 1 lithium, so lithium integrates into the carbon. The volume change is small, the structure change is small, so it's highly reversible. That's how you have your cell phone and laptops batteries working so well. But to look at one example such as silicon, it stores 10 times more lithium. But the volume expands too much once lithium coming in and going out. This volume change is too big. It's going to completely destroy these materials. So when we look at this problem several years ago, so my group came up with an idea comparing in the existing technology using the film, the big particle to make a lithium-ion battery electrode onto a metallic current collector. Instead, we grow nanowires of silicon out of this current collector. And under this structure, you can shoot the electrons in, take the electrons out. You can put the lithium ions in, take the lithium ions out. They expand, they contract, you can relax the strain, they don't break, so you solve the mechanical breaking problem. Well, that turned out to be an extremely exciting idea. Now the progress has been made. A lot of progress has been made, and now this technology is really, really close to a market application. It's in the stage of scaling up this process, try to push it to the low cost, extremely exciting. So I'm going to skip the detailed data for the time consideration. But I would like to mention, once you understand the problems related to certain material, certain technology, there's a number of different ways to design the right technology, the right material to address the problem. In the past 4 years, we have been doing all kinds of nanostructure, including the core shell structure, hollow silicon structure, try to overcome the problem of silicon. These are all very promising to address the problem of silicon and make it into very close to the real world. So I would like to also mention the cathode part of the problem. A battery has 2 electrodes. One is negative, the other is positive. Silicon is for the negative electrode. You would like to do the positive as well. My group has been working on trying to make the sulfur electrode to work. And this is a very exciting time. The Senate just passed a bill that they would like to do a battery hub, nationwide, a battery hub, is a $125 million program trying to address some of the most challenging problems related to batteries. Sulfur is one of the exciting materials. It is very similar to silicon, having a lot of problem, volume expansion, among many other problems. So we have been designing this porous carbon material to encapsulate sulfur, to try to make sulfur to work. So I'm going to skip through this. And also on this campus, it's very common for students to notice a lot of collaboration between different groups. This is an example of collaboration between Hongjie's group and my group. I try to, using the graphene from Hongjie's group to encapsulate sulfur to make sulfur to work. This is actually very exciting progress. Let me skip the detailed data. And time is running up. Let me mention something else also. In the energy storage research, you see some examples, but let me mention also one thing. Professor Michael McGee is going to talk about solar cell, but I'd like to mention just one slide. And recently, we just brought in a large consortium called Bay Area Photovoltaic Consortium. This consortium is led by Stanford University and co-led by UC Berkeley. I just happen to be the co-director of this consortium with Ali Javi and Berkeley. Executive director is John Banner. The idea of this consortium is try to do PV manufacturing-oriented research, try to help the US solar company to reach the goal at the module level, 50 cents per watt. To really get to there, you look at the fundamental solar cell structure, you need to worry about every single component in this solar cell. We have the thrust to looking at starting from encapsulation, the outside part of the solar cells, to nanoscale photon management. When the sunlight comes in, how do you absorb all the sunlight photons? To the new type of transparent electrodes, absorber layers. How do you do the substrate, nanotexture the substrate, to enhance the photon management and advanced materials characterization, as well as reliability. Your solar cell needs to last 30 years. So we have faculties at Stanford right here, and also in UC Berkeley and SLAC and Lawrence Berkeley Lab and NREL, try to team up to tackle the problems in these areas. I believe there will be a lot of opportunity for the students to join in to play an important role in this process. Let me end my talk right here.